Welcome back. Welcome back. So, we talked about calorimetry as a way that we measure the amount of heat transferred in a chemical process experimentally. And now we'll talk about how we would do it, how we can calculate it, say if we already have experimentally determined enthalpy changes. And this is what is called Hess's law. So why we use Hess's law? There's some reactions that may be difficult or impossible for us to actually do experimentally, right? And so instead, we can use experimentally determined values for different steps of the reaction to calculate the overall change in enthalpy. So this is Hess's law. It says if a process can be written and replace process with reaction, right? If a reaction can be written as the sum of two or more stepwise reactions or processes, the enthalpy change of the total reaction equals the sum of the enthalpy changes of the various steps. What does that mean is what you might be thinking. So we'll do an example. If I summarize this, essentially what we're saying is when we write a chemical reaction, we write it as though like it can make us think that this happened in one step. But in actuality, it may be happening in multiple steps. It usually is. A chemical reaction is taking place in multiple steps, right? And so according to Hess's law, if that reaction that we write can happen in two or more steps, then the enthalpy change for each of those steps can give us the overall enthalpy change for the overall reaction. And you might still be like, that summarized version is still confusing. We'll do an example. Before we jump into the example, the reason that we can use Hess's law, right? The reason it's valid is because enthalpy is a state function. Remember we talked about that. We said enthalpy and energy, right? Change in internal energy, delta E, delta H are both state functions. The enthalpy changes, they only depend on where a chemical process or reaction starts and end, right? Remember the path that we take to get there does not matter. This is what makes it a state function. So Hess's law can only be applied to properties that are state functions. So let's look at an example. We can think of a reaction of carbon with oxygen to form carbon dioxide, right? And we can think of it as saying, okay, we have carbon, it reacts with oxygen to form carbon dioxide in one process, right? It happens directly. Or it could happen in, say, two steps, right? So the direct process, we would write it as this, right? This is typically how you would see this reaction written, where we have carbon as solid or graphite reacts with oxygen gas to form carbon dioxide. This is the enthalpy change, the standard enthalpy change. The standard is that little knot, that's little circle up there, right? So this is what the direct process is. Now, if it's a two-step process, right? In the two-step process, first, carbon monoxide is formed, and then that carbon monoxide reacts further to form carbon dioxide. So here is the reaction for each step, right? We've got graphite reacting with oxygen gas to form carbon monoxide. And this is what the standard enthalpy changes for that reaction, negative 111 kilojoules. If you're into numerology, what do we think that means, right? Why do we have these 111? And it's step one, so it's really like 1111. So this is step one. Now, step two, carbon monoxide reacts with more oxygen gas, and then we get to our carbon dioxide. And this step, enthalpy change, is negative 283 kilojoules. So the sum of these two steps is what is shown here, right? And the sum is we're adding all of the reactants, right? So we have carbon or graphite plus 1/2 mole of oxygen gas here, plus carbon monoxide here, plus another 1/2 of oxygen gas here. So this is the sum of all of our reactants. And then we do the same thing on the product side. We add all of the products, which is carbon monoxide plus carbon dioxide. And when we simplify that even further, what we'll see is we have 1 mole of this graphite, 1/2 of oxygen gas plus 1/2 of oxygen gas is equal to 1, right? 1 mole of oxygen gas. Because carbon monoxide is on our reactant and our product side, it cancels out. So we don't show it in our net change, right? Or our overall reaction, and we're just left with carbon dioxide in our products. So this is what our net change is, right? Which is the same reaction that we would write if this happened in a single step, or how we would write the direct reaction. So according to Hess's law, the enthalpy change of the reaction will equal the sum of the enthalpy changes of all of the steps. So we're just going to sum, right? Remember, negative 111 kilojoules was our enthalpy change for step 1, plus negative 283 kilojoules from step 2, and that gives us negative 394 kilojoules, right? Which we see that's what we had in the direct reaction as well. The sum, right? The sum of each step is the same as the enthalpy change of the overall reaction, whether it occurs in 1 step or 2 steps, which is mathematical proof that enthalpy change is a state function, right? Because whether it happens in 1 step or it happens in 2 steps, we still end up with the enthalpy change of negative 394 kilojoules for our overall reaction. All right, that's Hess's law. That concludes our 2 methods that we talked about in measuring or determining heat flow: experimentally using calorimetry, and mathematically, right? If a reaction happens in multiple steps, we can calculate it using Hess's law. So in your experiment 3 with calorimetry, you will actually be doing this, right? You will be doing a reaction and experimentally determining the heat flow. And you will also use Hess's law as well. So we'll definitely be looking more into both of these ways of measuring enthalpy changes. All right. Peace.